In today's video, we will learn about surface tension, capillary action, and viscous fluid flow. Majority of us have seen surface tension in nature when we see an insect is able to skim over the surface of water without sinking below the surface line. If we look at our figure to the right, we see we are able to place a needle on the top of the surface of the water. Although the needle is made up of metal whose density is greater than the density of water, we would expect it to sink into the water. However, the needle remains on top of the surface of the water due to surface tension. We define surface tension as the magnitude of the surface tension force divided by the length along which the force acts. And we symbolize surface tension with the Greek letter gamma. When studying surface tension, there are two forces that must be considered: cohesive forces and adhesive forces. Cohesive forces are forces between like molecules, such as the forces between molecules of the same substance. And this is why we see rain droplets forming on a surface of a desk instead of spreading out evenly. Another force, the adhesive force, are forces between unlike molecules, such as those exerted by glass on water, which is responsible for the meniscus we see in a graduated cylinder. Understanding cohesive and adhesive forces, we can look at capillary action. Capillary action is observed when a tube with a small diameter allows liquid to rise in the tube due to adhesive forces that are greater than the cohesive forces. And we can calculate these forces with the following equation of gamma multiplied by 2 pi the radius multiplied by cosine of theta is equal to the density times gravity multiplied by pi r squared multiplied by the rise in the height of the fluid. Or we can rearrange the equation for h, which is seen below. When we think of viscosity, we're thinking about the viscous fluid flow. Viscosity refers to the friction between layers, and that the velocity of the fluid is greatest at the center, since adhesive forces flow down the fluid on the outside. So the difficulty for one solid surface to slide past another, if there is a highly viscous fluid between them, requires a external force applied to move one solid surface that is equal to the force is equal to our Greek letter n multiplied by our cross-sectional area times the velocity of our fluid divided by the distance. By using Poiseuille's law, the flow rate of volume per time is a result of different pressures that allow the fluid to flow through the tube. When there is a pressure at the left end and a pressure at the right end. So by using this law, we can calculate the rate of flow. If we look at our first example, we see we have glycerin that flows through a tube of 1 centimeter radius. If the ends of the tube are 5 meters apart and a pressure difference of 3.0 times 10 to the 4th Pascal is maintained between the end, find the volume flow rate. And eta for glycerin is equal to 1.5 pascals multiplied by seconds. So we can summarize the information we're given. We're given that the radius is 1 centimeter, or 0.01 meters. The length of the tube is 5 meters with a change in pressure of 3.0 times 10 to the 4th, and our value of eta for glycerin is 1.5. And we're asked to find the volume flow rate, which can be expressed as Q. So our equation for our volume flow rate is equal to pi times our radius raised to the 4th power times our change in pressure divided by 8 our value of eta times our length. So if we plug in the values we're given, we see that our radius was 0.01 meters to the fourth power times our change in pressure of 3.0 times 10 to the fourth divided by 8 times the value of eta, which is 1.5, multiplied by our length of 5 meters. And when we do so, we see that our volume flow rate will be equal to 1.6 times 10 to the negative fifth meters cubed per second. In our second example, we see we have whole blood that has a surface tension of 0.058 newtons per meter and a density of 1050 kilograms per meters cubed. And we're asked to what height can the blood rise in a capillary blood vessel that has a radius of 2 times 10 to the negative 6 meters if the contact angle is 0. So if we summarize the information we're given that the surface tension is equal to 0.058 newtons per meter with a density of the fluid being 1050 kilograms per meter cubed, while the radius of the capillary blood vessel is equal to 2 times 10 to the negative 6 meter, and the contact angle is equal to 0. We're asked to solve for the height that the fluid rises. So for surface tension, we have the equation where gamma multiplied by 2 pi our radius multiplied by cosine of theta is equal to the density of our fluid times gravity multiplied by pi r squared multiplied by h. Since we're trying to solve for our height, we can rearrange the equation to get our h by itself. And when we do so, we'll get the equation where gamma multiplied by 2 pi r times cosine of theta divided by the density of our fluid times gravity multiplied by pi r squared. We see that our pi's cancel out. We see our radius cancels out and we're left with one value for our radius on the bottom. And so we can plug in our values. So we have our surface tension of 0.058 times 2 times the cosine of 0 divided by the density of the fluid multiplied by the force of the acceleration due to gravity times the radius of the blood vessel of 2 times 10 to the negative 6. We multiply this through, we see that the height that the fluid will raise through the blood vessel will be equal to 5.6 meters. Finally, in our last example, we have a block of ice that is drawn over a surface lubricated by a layer of water that is 0.1 millimeters thick. We're asked to determine the magnitude of the force needed to pull the block with a constant speed of 0.5 meters per second at a temperature of 0 Celsius, with the velocity of the water having the value of eta equal to 1.79 times 10 to the negative third newtons times seconds per meter squared. So we know we can solve for our force with the equation that force is equal to eta times our area multiplied by our velocity divided by our distance between the layers. So we're given that eta was equal to 1.79 times 10 to the negative third, and that the area of our block can be calculated by taking the width times the length, which is 0.8 multiplied by 1.2 meters to give us our area, and we're given that our velocity of the block of ice is 0.5 meters per second, divided by the thickness of our layer, which is 0.1 millimeters. And if we convert this to meters, we see it will be equal to 0.1 times 10 to the negative third. And if we calculate this out, we see that the force needed to slide the block of ice will be equal to 8.6 newtons.